this case, they're both going off in the same direction towards infinity. This is also true if they were both going in the same direction towards negative infinity, if they were both less thans. But either way, they're going in the same direction, so they're heading in the same direction. There is a part where one's alone and then they start to overlap, just like before. Do we care about the overlap? Not with the word or. If this were the word and, if this said and, then where would our solution start? At -6 or at 0? At 0. If this were the word and, our solution would start where they overlap, which is 0. And if this were and, would 0 be included? Yes, because it's true for both the green and the pink, because this is a bracket here. Now, if this were a parenthesis, then we would start at 0, but 0 wouldn't be included. But this is the word or, so our boundary actually starts where? At -6, right, because it includes everything. All the stuff where this is alone plus the stuff where it's together. So this is our working graph. This is not the final graph because we don't want all this other stuff going on here. Our final graph is from -6 with a bracket. Everything's included up in the direction of infinity. Okay. Which sort of engulfs and includes everything that's greater than or equal to 0. Oh, to infinity. Yeah. You will never have no solution for your ors, for your unions. Okay? You'll never have all real numbers for your intersections. So you can contrast those three possibilities. All real numbers, everything included but with a gap, or everything going in one direction so you're going off to infinity or negative infinity. One of those three things will happen. Okay with that? Okay. Now everything we looked at so far, 2.10, compound inequalities, and 2.9, simple inequalities, all of those are linear. Okay? Linear. All linear. Everything we've looked at so far is linear. They are not, and what we're about to look at is absolute value, and absolute value is not linear. So be very aware when you're doing a problem. It's easy to get this mixed up at first when we're starting to kind of do mixed problems and all. If there's no absolute value bars, it is linear. And you saw that just like we've been doing so far in 2.9 and 2.10. Okay. If there are absolute value bars, then you've got a little different meaning to that, if it's nonlinear. But it's going to parallel. What we're about to do is going to parallel a lot of what we've already done, but you've got to be very aware when you start, oh, this is linear, this is absolute value. It's two separate things. Don't imagine or solve like they're absolute value bars if there are no absolute value bars. Okay. And you may be like, what's she talking about? But when you start doing homework and doing mixed problems and all, you might start to notice, oh, I assumed that was one thing because I was already practicing that other thing. But it's not. Okay. It's a mix-up I commonly see when I do all of this sort of on one test. Okay, so 2.11, now we already did 2.11 at the beginning of the semester. Now, I'm not repeating a homework for this, but if you're a little shaky, I'm going to do a quick little warm-up review on this because it's going to tell us how to do 2.12. If you're shaky on this, make sure you go back and practice some of those problems. It will be on the final exam, and it's also going to be what is going to help us do 2.12 now. And, of course, that homework is long closed. It's from the beginning of the semester, but you can still go to it through View My Grades. So absolute value equations. Okay. And an absolute value equation is of the basic setup that if you've got an expression, and I'll write it as a big X because it could be any expression. It could just be a little x, or it could be a 2x, or it could be 5x minus 3. Some expression is inside AV bars, absolute value bars. And it is equal to some number. Now, when you have that set up, you are going to break it into two linear equations. Linear. This is not linear. But to solve it, you break it into two linears. You say you take that expression and set it equal to negative c, and you take that expression, you set it equal to positive c. And you solve those two linear equations to get your solutions. Now, so a reminder, a backup to that, let's think about this. If you had, and I'll just use little x, just a very, very simple absolute value equation. So the absolute value of x is equal to 3. Now, think logically, what values of x would make this true? What could x be that would, the absolute value of that x would be positive 3? Yeah, 3, right? And what's another value it could be? Negative 3. For absolute value equations have two solutions. Because there's two possibilities for what's inside the absolute value bars that's going to spit out a positive number. Both the negative version and the positive version of x will spit out a positive 3. So your solution is drop the bars and set it equal to the negative version, the positive version. Now, this is a simple x, so you're done. If there's something more, you'd continue solving till you solve for x. But the idea visually is that there's an anchor point. Now, you don't have to identify what the anchor point is. We discussed this more at the beginning of the semester. So it's kind of good for a visual thing, but it's not like you have to figure out the anchor point for everything you're working on. If there's nothing else here with added or subtracted the x, your anchor point is 0. Okay? And all this is saying is the absolute value of x equals 3 means this is 3 units. Your solutions, this is not your solution, but rather your solutions are 3 units from your anchor point. So your solutions are x, and the distance of one solution to the anchor point is 3, and the other is negative 3, because this is 3 units. 3 units to the left of the anchor point is negative 3. There's one of our solutions. And 3 units to the right of the anchor point is positive 3. There's our other solution. Absolute value gives us two solutions because from whatever our anchor point is, we can move left this many units, c units, or from our anchor point, we can move to the right, c units. Okay? And moving that many units to the left gives us one solution, and moving that many units to the right gives us another solution. And we're just moving from whatever our anchor point is. And the way to solve that without even having to worry about, well, it's my anchor point and visualizing everything, because you get bigger, more complicated numbers, and you don't want to rely on just visually putting that on a number line, is that you are solving, you can drop the bars. It's absolute value right now, which is not linear, but when we drop the bars, we can do that as long as we make two linears. The expression equal to c units to the left, so we write that as negative c. This means this many units to the left. And also, that expression equal to this many units to the right, positive c. So, for example, you've got the absolute value of x plus 4 is equal to 9. Okay. Now, I know just by looking at that my anchor point, use that as an A, my anchor point is negative 4. Okay. You don't have to know that, but it's going to help visualize when we see the solution. And this is also then going to help with our inequalities. Okay. So, do I have it in the correct form? Is there anything being added or subtracted to the absolute value I need to move over? Outside the bars? No. So that means I'm in the proper form. Until you're in the proper form, you can't drop the bars, but now you can drop the bars into two linears. Drop the bars and move 9 units to the left. Drop the bars and move 9 units to the right. And you're moving 9 units to the left of your anchor point, and here you're moving 9 units to the right of your anchor point. Now, if I move 9 units to the left, negative 5, negative 6, negative 7, negative 8, negative 9, negative 10, negative 11, negative 12, negative 13, negative 14, etc. I got to negative 13, so bless you. 5, 6, 7, 8, 9, 10, 11, 13, negative 13. Okay. So that is 9 units to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9. That'll be 5, because I'll do negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. So 9 units to the right of my anchor point is my other solution. All your anchor point is, if you want to visualize it after the fact, is it's the halfway point between your left solution and your right solution. Okay.
So is it going to be always the number with the x, so you put this sign?
Yes, unless there, well, the anchor point is the setup algebraically is x minus b, or so let me use the a, x minus a.
So it will always be.
Well, if this were x minus 4, then your anchor point would be positive 4.
Oh, okay.
Yeah, because the setup is x minus a, so this is like x minus negative 4. Yeah, but if you have a coefficient on x, that expands or contracts things, so that changes things. So that's why this is good visually if you have no coefficient here. It's visual for understanding why absolute value has 2 solutions. But there's no reason to lean on that moving forward. It just helps sort of understand why does this have 2 solutions. Well, because you've got this middle point, your solutions are this many units, C units, from that middle point. C units to the left and C units to the right. So our solutions are negative 13, which is 9 units away from the anchor point to the left, and positive 5, which is 9 units away from the anchor point to the right. Now, if you plug these back in, you'll see it makes it true. Negative 13 plus 4. It's negative 9. And what's the absolute value of negative 9? Right. Now 5 plus 4 is 9. Absolute value of positive 9 is? Right. There are 2 values of the 2 solutions because one of them is going to make the negative version, which becomes positive because it's absolute value, and the other is going to make the positive version, and the absolute value of that is also positive. So 2 possible things can make 9 or negative 9, and the absolute value of that gives you 9. So you can check your solutions, but that's why you have 2. Right. So that's why this is not linear. The related graph of this 2-variable graph makes a V. As you move to college algebra, this will be one of our families of functions other than linear that we'll look more closely at. We'll try one more, and then we're going to move over into the inequalities. 4x minus 1, absolute value of, plus 9 equals 11. Make sure you're in the proper setup, or it will be wrong. If you don't start off with the proper setup, it's wrong after that. So make sure you have absolute value only equal to a number. Do not drop the bars until you have that set up. Your 2 solutions might both be positive, both be negative, or it might be a mix. The solutions, x, can be anything, positive or negative or 0. That doesn't matter. What matters is the right-hand side can't be negative because whatever gets spit out of here, positive or negative values might make this just fine. Once you apply the absolute value, it's that C before you start that must be positive.
And if it's not this bad?
And if it's not, say no, I'm going to show you exactly. Yeah, that's. I'm glad you brought that up. What if we have this? Yeah, it's not that it's the mathematical way to put it is there any value of x that can make this true? Anything you put in here, no matter what you put in for x, once you apply the absolute value, what kind of answer are you going to get? Positive, yeah, or 0. Yeah. You might, if you put in negative 8 here, you'd have the absolute value of 0, which is 0. So your answer is going to either be 0 or positive. It's going to be non-negative. So is it ever possible for this to be negative? No. No matter what x is, the absolute value of whatever this is is going to come out 0 or positive. So this is impossible. Another way to think of it is that absolute value is distance. That the very definition of absolute value is distance. Distance from an anchor point. And distance, I might move left or I might move right, but distance is always positive. Okay? I use the negative and the positive to show left and right, but distance itself is always positive. So when I'm talking about distance, when I still have the bars up, I'm saying the distance is 2 units. You'd never say distance, absolute value, the distance is a negative amount because distance is always positive. Once I take away the absolute value bars, I took away the word distance, and I use the negative to say 2 to the left, 2 to the right. And that's good. But if you start off with the negative when the absolute value bars are up, you're saying the distance is -7, and that doesn't make sense. Distance is always positive. Okay? And absolute value of anything is going to be non-negative. So we would just say this is no solution. And don't do anything. Okay.
And that rule applies always when the constant thing.
Yes.
Don't
Always.
even try to solve it.
Huh?
Don't even try to solve it.
No.
Okay.
Nope. If you did, and then you plugged your answers back in, you'd see they're wrong, but a lot of people will just go ahead and try and solve it, but not check their answers, and then, because it looks like you can solve it, but you can't.
But it's okay, you do try to solve it if there's a number on the outside of the distance line?
Well, yes, if there was a number over here, you mean, you would move it over here.
Okay.
Now, you can't decide if this is positive or negative until anything that was over here outside the AV is moved over. It might look negative, but if I had a -9 here, then I'd be adding 9 over here and become positive. So don't make that decision until you're in absolute value equals a number. And then if this number is negative, you're done, walk away. No solution.
So say like it was +2 and then you got to do a subtract 2 on both sides.
Uh-huh.
That's where it would still be 0, right?
It would still be null. Yeah, it would still be no solution, right. But you can't make that decision until it is in the proper form. Absolute value only is equal to C. A number. And if that C is negative, no solution. It might look negative to start with, but if you haven't isolated yet, you can't tell. Okay, so here are 2.12 absolute value inequalities. And absolute value inequalities, we're going to, I'm coming back to these 2.9 notes that we started with. Here's a linear equation. And that linear equation, we get an x equals that, we get a solution. That is the solution. When we plug it in, it satisfies the equation, and we write our solution, our one solution in set notation. That's a linear equation. And if you write linear inequalities, what you get is not the solution, but rather the boundary point, which was, because we used the same numbers, was still 3, but instead of 3 being the solution, it's the boundary point or the edge of the solution. And you have infinite solutions rather than just one solution, you have infinite solutions. Now these are all linear, as I pointed out. It's all linear we're dealing with. But now with absolute value, this is nonlinear, but it's got the same sort of setup. Okay? So if we have x plus 5, sorry, x plus 3 is the one I was using. X plus 3, absolute value of, is equal to 5. Actually, I'm going to use a little bit bigger number just because I want it to be easier to graph. So yeah, let's do x plus 4 is equal to 5. And so that's an absolute value equation. So I'm going to drop the bars and solve two linears. X plus 4 is equal to -5, 5 to the left, and x plus 4 is equal to 5 to the right. To get my two absolute value solutions, distance to the left, distance to the right. So I've got x equals -9, and x equals 1. Now, on a graph, I would say that's a solution, and that's a solution. So if I draw a number line and put it, it'd just be 2 dots, not the in-between numbers. And that's why we don't bother putting on a number line. It's pretty basic. Okay. And so, in set notation, just like a linear would have one solution, absolute value has 2 solutions. Negative 9 is one of the solutions, and 1 is the other solution. Okay. Okay. Now, if we take that same number, the same expressions, and again, these are not linear like we had before, but rather they're absolute value. But we're going to see the same sort of pattern. Here we got one solution for linear. For absolute value, write two solutions, set notation, and we're done. But if we write the same expressions but with inequalities, we're not going to be finding the solution. We're going to be finding the boundary points of the solution. So x plus 4, absolute value of x plus 4, less than 5. Okay. So in order to, I find that the easiest, there's a couple approaches to this, and the book teaches it a little bit differently maybe. But I find the easiest approach to this is just like you recognize that with simple linear inequalities, then your solution is just the boundary point, is the same thing with absolute value. We want to find our boundary points, and then we just look back to the inequality symbol to tell us what happens with those boundary points. What part of the graph do we shade in starting at the boundary points? The inequality symbol and the direction of it will tell us which way. But first, let's find the boundary points. So take your linear inequality and just write it as an equation, because you already know how to solve an absolute value equation. And that's going to give you your boundary points. So, of course, we solve it just like we did here already. And we got x equals negative 9 and x equals 1. Now those right there are, again, not the solutions. This is two solutions. Those are the actual solutions. We put in set notation. These are not the solutions. Rather, these are the boundary points, okay, of the solution. Okay. So I'm going to draw a number line. It's my negative 9. So, my boundary points are where my solutions begin. Now, just like there are two solutions with the equation, there's going to be two things drawn with the inequality. Just like there's one solution here, that's the boundary point, and then the solution for the inequality either goes off to the left or off to the right. Okay? Well, my solution here is going to start with my boundary points, and they're either going to start at the boundary points and move in, or they're going to start at the boundary points and they're going to move out. And here's the way to think about it. This right here is less than. Okay? Now, less than will always mean and, or as also and means intersection. Okay? So all that we're concerned about here is overlap. Now, whether it's less than or equal to, but the less than, pointing down the number line, is going to be our and. This is equivalent to our intersection in 2.10. Okay? Except in 2.10, we weren't dealing with absolute value bars, but absolute value bars are just another way to write a compound inequality. Okay? So this is a compound inequality of the intersection variety. Now, visualizing it like this means the distance between x and the anchor point. Okay? So our anchor point is negative 4. Okay? There's our anchor point. I'm not really drawn to scale here. But our anchor point is negative 4, which means our solutions, negative 9 and 1, are 5 units away. 5 units to the left of the anchor point, 5 units to the right. Okay? So if this were just an equality, our solutions, negative 9 and positive 1, are 5 units away from our anchor point of negative 4. Here, though, our solutions are not equal to 5 units away from the anchor point. They are less than 5 units away from the anchor point. So all of our solutions, all the values of x, must be less than 5 units from the anchor point. So am I going to color in between the numbers or pushing away from the boundaries? This 9, negative 9 right here is 5 units away, but I want my solutions to be less than 5 units away. So would I go to negative 10 or would I go to negative 8? Yes, I'm finding all those things that are less than 5 units away from my anchor point. And less than 5 units away from 1. So that would be this way. All of these things right here are less than 5 units away. That's like our overlap. Okay? So this is all of these things in between our boundary points are less than 5 units away from the anchor point. Less than or equal to pushes in towards that anchor point. It converges in. It's the chunk of the number line. And all of our solutions are less than 5 units, so they move inward towards the anchor point. Now, are boundary points included or not included in this example? Not included. So we'll make sure we use parentheses at our boundary points. I'm going to take that 0 off just so it's not. So our boundary points are -9 and 1. They are not included, so we use parentheses. And the less than symbol tells us that all of our solutions fall inward. Now, if we have x plus 4, absolute value of greater than or equal to 5, we're going to write the equivalent equation so that we can drop the bars. First, we would isolate if we needed to. And then we write it as an equation, and we drop the bars and write our two linears and solve them. And of course, just like we did here, we got x is -9 and x is 1. And those, because this is an inequality, those are not the solutions, those are the boundary points. Okay. Boundary points, boundary points. Oh, and by the way, our solution here is, of course, -9 to 1 in interval notation. And so here, we'll mark where our boundary points are. -9. That would be our anchor point. That you don't have to mark your anchor point. It's just visually so we can kind of see where we're moving. Okay. So there's our solutions, our boundary points. Okay. Now we look back at our inequality symbol. Now this inequality symbol is greater than. And greater than is equivalent to or, also known as our union. Okay? And instead of an overlap, it includes everything. Okay? So absolute value inequalities are just a way, a shorthand way to write it won't work for everything, but a specific kind of compound inequality. And with less than, we've got the intersection type of compound inequality. And with the greater than, we have the union type of compound inequality. So these are our boundary points, and what this is saying, the greater than is saying that our solutions are more than 5 units away from our anchor point. So if this is our anchor point, this is how many units away, up to 5 units away is 1, but we want anything greater than 5. So when we started our anchor point of 1, is our solution, do we color in to the right of it or to the left? We want our solutions to be greater than 5 units away. So 1 is 5 units away. So to the right, yeah. Everything to the right. Now is 1 included? In this case, no. So we'll put a parenthesis there at 1, and everything's pushing away. Now in the other direction from the anchor point, -9 is 5 units away from our midpoint, our anchor point. But we want all the solutions that are greater